Let's work with the stress transformation equations in a numerical example. And we'll start with one that has a whole complex series of stresses, right? On the x-plane, we've got 1400 in compression, and on the y-plane, we've got 1000 in tension. And then we've got the state of shear stresses such that these are 500 and they are at what would be considered to be a negative value, right? And so we want to take this as our given conditions, and we want to find out what the normal stresses and the shear stress are on a inclined plane that is oriented with 3 on the rise, 4 on the run, and it's kicked off sort of up to the left. All right, so that's what the first thing we'll do is we'll figure out what the angle is that we need to be working with, right? So let's start by showing our coordinate system. And I'll just start with the x and the y axes, right? There's your x and there's your y. Our plane AA then runs like this. And again, that's a 3 on 4, where the little tiny angle, right, inverse tangent of 3 over 4, that angle right there is 36.87 degrees. Really 869 change, blah, 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 but about 36.9 degrees. Now, the question that always comes up is, well, is that our theta or not? And the answer is to always go look at the normals. All right, so we're going to start with a plane that has the x outward normal, right? And so here's the vertical, it's really a vertical plane here. And you've got to swing that not to there, but we want the normal to the plane of interest. So that goes all the way around to there to get to the one that we actually want, right? So let's draw that outward normal. That's the one we want. Notice that this skinny angle, the 36.89, is right in there. And so the total is what we want. That's your theta. So theta is equal to 36.87 degrees plus 90 degrees, right? The little angle plus swinging at the final 90 degrees, that's sitting right there. And so that makes it 126.87 degrees for theta, right? That's usually a place where people make mistakes, right? The x is a normal. We got to go from like to like. So normal to normal, not normal to the plane, but normal to normal for that angle. So that's one of the key steps. Then another one is to define your stresses. And by that, I mean sigma x, sigma y, and tau xy, including their signs. That's particularly crucial, right? So sigma x is in compression. That would make it negative. So that's a minus 1400 psi. Sigma y going in a tensile direction then is a plus 1000 psi. And then tau xy is going to be a, well, it's 500, and it's going in the opposite direction of the shear stress positive sign convention. So it's a minus 500 psi. Those are crucial steps here in terms of getting the signs correct. And I just always go back to, we've got our x and y's are outward, right? And the shear stresses are positive by pointing to the other positive direction, right? So here sigma x is going that way. That's your positive. For tau xy on the x plane, but going to the positive y, well, we got to go up. For tau yx, positive y plane, and we got to go to the positive x, it goes that way, right? And there's your sigma y. Down on the other ones, right, these are sort of the opposite ones, the negative global x direction, the global negative y direction. So we go from the negative y to the negative x to the negative y, to get those all oriented in the correct directions as well. how I tend to think about it, right? Once you have these, all of this stuff, now it's just a matter of putting them into the stress transformation equation, right? So we're going to write out one of these. Let's find the normal stress first. And so we would have then that sigma n is equal to the average of sigma x and sigma y. That's the first term in that expression, plus the difference between those two divided by 2 times cosine of 2 theta plus tau xy times sine of 2 theta. And now we got to put all the numbers in there correctly, including their algebraic signs. To not do that correctly will mess everything up, right? So the first term, that average includes then a minus 1400 plus 1000, all divided by 2, and then quantity plus of the difference, so that's minus 1400 minus 1000, all divided by 2, times cosine of twice theta, right? So 2 times 126.87, which would be pretty easy to do, but there you go. I've got it in memory for you, right? That's 253.74 is what that angle would be. And then plus tau xy, but tau xy is a minus value, it's minus 500, and then times sine of the 253.74, which was already the double angle, right? So sigma n, when we do that work, is going to do all the math, and we'll get a positive 616 psi, and that's darn near exact. 16.6.000, so on and so forth. That's your normal stress value on that plane, right? Then we got to do the same thing for the shear stress. I need to find the eraser here. And so let's find our shear stress value. On that plane. That expression will be minus, now I gotta have to cheat and look this up again, right? It's minus the difference term. Sometimes you don't see the minus sign in there, they just swap the sigma x and sigma y, so you gotta be careful there. Times sine of 2 theta, and then plus tau xy times cosine of 2 theta. Do the same thing, put all the numbers in there, and you're going to get a, well, let's put them in there, because I all of a sudden don't remember. I know it's 1016 or something like that, but I don't remember if it's plus or minus anymore. So minus a minus 1400 minus the 1000, all over 2 times sine of our 253.74 degrees, and then plus tau xy, which is in itself a minus, so minus 500 times cosine of 253.74 degrees, right? I can see I'm going to have to erase again, no big deal. So let's do that. And again, I know the raw number, but I don't remember the sign, so let's see what we've got. We've got minus 2400, that's divided by 2, minus times a minus, so that's already, that becomes a positive, 1200 times sine of 253.74, sine of it, and then minus this business, minus 500 times that angle cosine of, and we get a minus 10, 12. So ton T equals a minus 10, 12 psi. So then we have to figure out what that means in terms of how the stresses are acting on the plane. You know the plane is oriented like this, right? If we're driving to the right, we're going uphill. And we got there by swinging from here to there, right? So that means that we're going from here, here's that normal, right? X all the way to there. So that means that positive there is going that way on that surface, and that's the 616. Now the shear stress, now it's represented by thumb, we come all the way over and boom, there, so that we got an opposite number. That means it looks like that, right? So take the right hand, all the way over to their plane, and it was opposite of that, so it rotated and went that way. Which does mean that if we want the ones on the other side, they'll be exactly opposite of those and would look like that. The angle would change here to get there at that location. Now, later, when we know more circle, we'd be able to come up with all this and actually be able to figure out which direction this is way faster than punching it into our calculator and doing all this work. There's shortcuts here. Not only doing the math, but also interpreting it becomes much more reliable when we learn the technique of more circle. So we'll come back to this one and see what that all looks like.